Hello everyone, welcome to today's video. We're going to talk about linear systems of equations. We'll compare them and try to reinterpret them with the new linear algebra objects and tools that we've been developing in this class. Before we do that, let me remind you of a few features of linear systems of equations. Let's look at this example here. This is an example of a linear system with two variables and two equations. I want to keep it general, so I will call the coefficients suggestively as a11, a12, a21, and a22, and the constant terms will be named b1 and b2. In two dimensions, you should remember that there's three possible outcomes for this linear system. Every one of its equations correspond to a line in the plane, and depending on the reciprocal positions of the line, we have three different scenarios. If the lines intersect, they will intersect exactly at one point. We'll get a unique solution to our linear system. Or the lines may be parallel, that's scenario 2, in which case there's no solution to the linear system. Or the lines could coincide, in which case we have infinitely many solutions to our linear system. We will say that whenever a solution exists to a linear system, scenarios 1 and 3, the system is consistent. And we will call it inconsistent if there are no solutions, like in scenario 2. What we're going to do next is to translate our knowledge about linear systems into the linear algebraic language. Let's do so in an example. Here's a linear system with three variables and three equations, and I want to rewrite it using our knowledge of matrices and vectors. In particular, let me rewrite it like this. I can collect all of the coefficients in front of x1 as follows: 1, 1, and 2. And then I'll write the same thing for x2. The coefficients are 2 in the first row, 1 and 1 in the second and third. And then I'll write x3 times a vector of its coefficients, which are 1, 1, and minus 1. All of this is equal to the vector containing the constant terms. In this way, we wrote an equation whose constant terms are no longer numbers, but they are vectors now. And that's a trade-off for reducing from 3 linear equations to just 1. Now we have 1, but with vectors in it. We can condense this writing even more by considering the fact that this left-hand side is a linear combination of the vectors that are present here, 1, 1, 2, 2, 1, 1, and 1, 1, minus 1. Since it's a linear combination of those, I can write it like this. I can write it as the product of a certain vector, x1, x2, x3, multiplied on the left by the matrix whose columns are the vectors that I wrote up here, the vectors containing the coefficients of our linear system. So our equation now reads a matrix multiplied by a vector of variables equals to a vector of constants. And this is how we will write linear systems from now on. Ax is equal to b, where x is a vector of variable. We can condense this writing even more by containing or packaging all of the information in the linear system into a matrix that will be called the augmented matrix. This matrix here is just obtained by remembering the matrix of coefficients, and then to the matrix of coefficient, sticking on the right here the vector containing the constant terms. So notice that when we started from a matrix A, which was a 3 by 3 in our case, the augmented matrix will have one block that looks like A and one extra column. So its size is going to be 3 by 4. The way we'll work on the augmented matrix will reflect the usual steps that we would take into solving the linear system, manipulating the equation. What we'll get by those manipulations of the equation on the side of the augmented matrix are called elementary row operations. Let's have a look at them in this example. I recalled here the linear system and the corresponding augmented matrix. If you were to solve this linear system, there's many steps that you can take, but one possible one would be to try and take the second equation and subtract it from the first one. Doing so would eliminate the variables x1 and x3. And that suggests that it would be a good move to solve the linear system. Let's try it, and let's do it here. If I subtract these two rows, which I've written here, x1 plus 2x2 plus x3 equal 5, that's the first equation in our linear system, minus x1 plus x2 plus x3 equal 2, I get 0 plus x2 plus 0 is equal to 3. In other words, writing without the zeros, I get that x2 is equal to 3. Now, I can reflect this into the augmented matrix. The augmented matrix that we started from is up in this corner here. What we did to it was, well, we didn't touch the last two equations, and by the same token, I will not touch the last two rows of the matrix, but I can replace the first row by whatever I get by taking the first row of the matrix and subtracting the second row. The result of that is the following row, 0, 1, 0, 3, which exactly corresponds to this equation over here, x2 equals 3. Similarly, we can proceed further to solve our linear system. Another thing that we can do, and we can either look at it from the point of view of the linear system here, would be to add together the second and third row, because that would eliminate variable x3. Let's try to compute what that would mean at the level of the equations. The level of equations, I would have x1 plus x2 plus x3 is equal to 2. That's my second row. And I would have 2x1 plus x2 minus x3 equals 0. That's my third row. If I add these together, the resulting equation is 3x1 plus 2x2 plus 0 is equal to 2. I can do the same operation on this augmented matrix and add together these two rows. If I do that, the resulting matrix looks like this. One of the two rows is unchanged, and I will replace the other row by the result of adding them together. 2 plus 1 is equal to 3, 1 plus 1 is equal to 2, 1 minus 1 is equal to 0, and 2 plus 0 is equal to 2. The first row is untouched, and so we just copied it in the same way. If I were to look at equations again, what I can do now is to use the fact that I know that x2 is equal to 3. But let's look at this augmented matrix now. I could use the fact that x2 is equal to 3 to eliminate x2. And I can do that by, at the level of this matrix, by subtracting the first row from the second one. My second row, well, by multiplying the first row by 2 and then subtracting it from the second one. So let me write that like this. We have an equation coming from up here, which is 3x1, 2x2 equals 2. And from this equation, I want to subtract twice the first row, which tells me x2 is equal to 3. When I compute this result, what I get is, well, 3x1 plus, I would have 2x2 minus 2x2, that's a 0, equals 2 minus 2 by 6, 2 by 3, which is 6, negative 4. At the level of the augmented matrix, this reads as follows. We have the first row, it's unchanged. Then the second row is replaced by the following. 3x1, 0, 0, negative 4. The third row is not changed. So what I did here was to replace my old second row with something new, which was the second row minus twice the first row. To get 300 minus 4. Okay. Now, let's clean this matrix up. Well, first of all, notice that we have x2 is equal to 3. That's something that we found in the first step. Now we have this other equation here, which is 3x1 is equal to minus 4. In other words, x1 is equal to minus 4/3. And now we can use these to get rid of the variables in the last equation. The remaining equation is 2x1 plus x2 minus x1 is equal to 0. Let's write it at the level of matrices. We have 0, 1, 0, 3. Dividing the second row by 3 gives me 1, 0, 0, minus 4/3. And now I can take the last row and replace it with whatever I get when I write itself minus twice the second row, which will eliminate this 2, and minus once the first row, which will eliminate this 1. Let's write that down. My third row is now 2x1 plus x2 minus x1 is equal to 0. From this, I subtract twice the second row, which is x1 equals minus 4/3. And then I subtract the first row, which is x2 equals 3. When I total this, I get 0 here, 2x1 minus 2x1, plus a 0 here, x2 minus x2, minus x1 is equal to, and when I total the second side, I get 0 plus 8/3 minus 3. Let's write that at the level of the matrix, the augmented matrix here. That's 0, 0, minus 1, and 8 minus 8/3 is minus 1/3. I can now clean up this matrix a little bit by performing the following two operations. I like to swap the first and second row, because the first row now reads x2 is equal to 3, and the second row reads x1 is equal to minus 4/3. The third row is now minus x3 equals minus 1/3. That's what I read from looking at the augmented matrix here. Let's clean this up by just putting some order into them. So my second row will become the first row will be traded to the second, and the third row, I can multiply it by -1 to make it look nicer. If I read off this augmented matrix out here, what these rows translate to in terms of equations is that x1 is -4/3, x2 is equal to 3, and x3 is equal to 1/3, which is the solution to our problem. We did this example keeping equations and the matrix in parallel, but you can certainly solve these problems forgetting about the equations and just looking at the matrix. To do so, I just want to point out that what we performed are called raw operations, and there's only a few that we can do legally. There's essentially 3 manipulations that we can make. I am allowed to replace a certain row Ri in my matrix by a scalar multiple of it. I am allowed to replace a certain row Ri by itself plus the scalar multiple of another row, C times Rj. And the third legal operations that I can make is to switch rows within one another. These 3 are the elementary row operations. The reason why these are legal is that they correspond in matrix languages, in matrix language, to the steps that you would take to solve a algebraic linear system. From now on, we will stop solving algebraic linear systems, we will work with matrices, and we will perform row operations on them. In the next video, we'll study a procedure to systematically apply row operations to solve linear systems using augmented matrices. I'll see you in the next video.